session will be mapping seasonal interactions between population movements and malaria transmission, and by my co-chair, Andrew Tatum.
Thanks. I'm going to talk about some work that's in quite early stages, but is an ongoing collaboration between Southampton, the Namibia Vector, there we go, it's moved on already, and the Namibia MTC mobile telecommunications company. So we've seen already from Bobby's talk, there's multiple purposes here for mapping, identifying residual transmission foci, targeting vector control and case detection, and managing importation risk and outbreak control and post-elimination settings. And our focus here will be on Namibia, and really when we started working in Namibia 5 years ago, this is the kind of mapping that exists and is still very useful in stratifying the country for the program. We also have available the Malaria Atlas project maps. As we get down to the last few thousand cases, parasite prevalence becomes less of a useful measure. So there's been quite a lot of work in Namibia and other countries on developing higher resolution mapping of case-based or incidence-based. As Bobby showed, we can get together a range of sociological, ecological covariates that we can use in a kind of niche mapping model to identify areas that have similar characteristics to where we find local cases. And this is the output of that. And it enables us to go from a kind of existing homogeneous intervention deployment across the north to a more refined area where we can focus down on from 1 million to less than 0.2 million in terms of areas to target. But that really gives us just a static picture, when in actual fact there's a lot going on in Namibia. So this is the cases reported by health facility. We still see a lot not reporting, but that's improving. But we see some seasonal patterns, some strong ones, particularly recently, December, January, February, March. We see increasing numbers of cases. And it's this kind of information that has prompted extra approaches to try and exploit this kind of health facility-based reporting data. Of course, there's problems with that data, and those need to be accounted for. So the utilization of health facilities, positivity rates, and various researchers have tried to do this in the past. So this is some examples from Victor Aligana's work, fitting a model based on DHS treatment-seeking questions and travel time information to convert information from household surveys into a predictive model of facility utilization and catchments. And ultimately turning that through a conditional autoregressive Bayesian model into mapping actual monthly incidents, a much more useful metric for those countries that are getting down to low levels of cases. Just a quick advert for Hugh Sturrock's paper just came out yesterday as well, doing something similar for Swaziland. But we have the issue here that all of these kind of approaches assume a static denominator. The population stays the same year round. We know that's not true. So here's an example just from some mobile phone data from Côte d'Ivoire. This is just a sample of 500,000 people, and we see trips of up to 1 million trips to surrounding areas in a course of 6 months. In West Africa, we see such huge seasonal migration that we can see patterns from space, from nighttime light satellite imagery. So how, if we can measure this mobility, how does this actually change our estimates of incidence? So what we can use is a source of information, the mobile phone call data records. So you may make a call here, it's routed through the nearest mobile phone tower, and the network operator records that anonymously for billing purposes, the time and the tower of that call. If you move to a new location, you make another call, that is recorded again. And so across the millions of customers, we have this information on how people with mobile phones are moving around. So the data is not perfect, and different countries have different problems in terms of biases in usage, but it's quite an unprecedented data set in terms of how we can measure populations across time and space. So what we've done, this is France, this is not an elimination country at the moment. So this is the census data producing a population map from that, and we were able to quite closely replicate using call densities the population distributions, coming out with quite a strong relationship. And the benefits, of course, of the call data records are that they are continually measured, so we can come up with dynamic population maps. So this is population density difference between a typical workday and a typical day in August when most of the French are on holiday. You can see everybody going to the coast except for a few dots in Paris, of Asterix Park, Disneyland. And not only can we see those patterns on those broad time scales, but day by day. So this is Wednesday, Thursday, Friday, Saturday, and Sunday. Some huge movements, and then back to work again. And this kind of information is very valuable for France, but can also potentially be valuable in improving our mapping. So we were interested, was this kind of huge mobility in Namibia? And the answer is that, yeah, at certain times of the year, there is some huge movement. So this is quite a complicated graph, but the key thing here is this is callers per day on a log scale. So at certain times of the year, we see some huge movements. And this is from a sample of 2.1 million active subscriptions in a population of 2.3 million. So MTC has a pretty dominant position in Namibia, and we get a pretty good sample of movements. So combining these kind of data sets again, adjusting for biases, coordinating with the census data, we can again produce dynamic population maps. So this is the cases from 2012, 2013 for Namibia, showing the kind of dynamics of malaria seasonality in Namibia. And this is how the population dynamics change. So across December, we see a huge outpouring of people from Windhoek into the northern regions. If you look at the scale there, that's up to over 5,000 people per square kilometer density changes. As we get to January, it's reversing as people move back to work, to places where they live away from the holiday time. Again, this continues through a couple of months, and it kind of calms down a bit, but then holiday times come again, and we see some shifts in population. But again, some pretty large shifts. And the question is, how does this impact our measures of incidence? So again, we can map out those catchments as we did before, and look at how the population estimates change in those catchments. So here, a catchment of a health facility in Windhoek, huge changes across from December up to September, nearly doubling that population. A rural catchment here, we see from December to January a big change, and then just a few kilometers away, a few tens of kilometers away, another rural catchment where the reverse is true. In December, a huge number of people are moving in back with families in the places where they grew up. So how does this change our incidence? Well, if we just do a simple calculation of how our incidence estimates change from going from a static denominator to a dynamic one, we can see some quite big changes overall. So December, we may be actually overestimating our incidence by as much as 12%, whereas the reverse may be true in February and March. And just an example here of mapping those numbers out by catchment, we can see those numbers potentially change by as much as over 30% in some of these catchments because of the huge number of people moving in, diluting our estimates of incidence reporting from the health facilities. So this accounting for mobility in our mapping, I think we can use that to help us refine our mapping of case incidents. The final thing I'll briefly touch on is ongoing work that both parasite prevalence and incidence measures at the location we're measuring them at as a metric of intrinsic local transmission can be misleading because people can be infected elsewhere and then come back and report to their local health facility. So an example here, a population in settlement A which has a moderate level of transmission. Giant mosquitoes are a bit scary, but we'll ignore that for now. And two other settlements, B with a much higher level of intrinsic transmission, and C maybe an urban area with no ongoing transmission intrinsically. But that population in A may spend a proportion of their time in B and a proportion of their time in C, and then report when they are sick to the local health facility. So what we're seeing at that local health facility doesn't necessarily represent what's actually going on at location A. So this is ongoing work led by Dave Smith and Nick Ruktanonchai, but combining this mobility data from the mobile phone records with a simple multi-patch model looking at flows between those to come up with an adjustment of what may be actually going on in terms of intrinsic transmission. So this is some old data from the Malaria Atlas project on estimates of R0. So not a real representation of what's happening today, but just a conceptual test run here. If we account for mobility, we get a much more heterogeneous picture in terms of what may actually be going on, and that some of those areas may only be supporting transmission because of movement and people bringing infections in. And that difference map illustrates what we see there. Finally, the big elephant in the room here is the fact that there are huge cross-border movements, potentially from Angola, from Zambia. Ongoing work here is to try and can we actually identify from these anonymous phone record data who these border crossing populations might be and how they move about the country, because they're potentially high-risk populations if they're spending time in the areas to the north where control methods, intervention coverages are a lot lower. So here's an example of pattern recognition methods where a person who's making regular calls may move to the border, continue making regular calls, disappear from the records for a while, and come back again, continue to making communications. It's a very simplistic approach, but it's across the uncertainties we can come up with a probabilistic metric of who may be the border crossings and their movement patterns. So, just with 10 seconds left, we have shown mapping malaria transmission can be valuable in supporting these elimination programs. But existing approaches so far have not accounted for population dynamics, which appear across many mobile phone datasets, many other movement datasets to be substantial. There are a range of data sources now, particularly these call data records, for improving our understanding of the substantial dynamics that we see. And modeling frameworks can help integrate those mapping and mobility data to try and tackle some of these policy relevant questions. So next steps are ongoing validation with case data, developing these methods. New data, there's 5 years worth of mobile phone data now to test this across years, and extension to other countries. So a few acknowledgements of those organizations and people who've supported this work, and there's further information on these websites. So I'm happy to take questions.
While people might be coming up, how do you take into account age in this, in that children may be staying at the home base and might be the carriers? And
yeah, it's a very good question, and that we don't know anything about these populations. We don't really want to know anything about these populations. There's confidentiality issues in terms of mobile phone records. So we have to make a lot of assumptions here about who is moving and who they take with them. And we're working with various groups who are conducting travel history surveys, mobility surveys, that have more information on who those populations are, whether they're taking children with them when they make trips, and that will hopefully give us a better idea. But it's still a big gap in our knowledge.